First of all, I want to thank all of the judges who are here today. I think it really means a lot to all the faculty and as well as the students to have you guys come out and actually interact with our students and learn about the kind of research that we're carrying out here. So thank you very much. So today I'll tell you a little bit about what my group is working on in the area of nanoplasmonics. This is a picture of my group right here. We've grown a little bit since then. We've added a few new students. I started in the nanoengineering department about 4 years ago, so I'm still an assistant professor. I'm not an associate professor, but I'll take that promotion in your eyes. This is basically our concept for designing solid-state materials. It's a little bit different than how you would normally think about making a solid-state device. So in our group, we think about how to build materials using nanoscale building blocks. So in this case, we look at particles made out of metals and semiconductors and design them with specific sizes and shapes. And then we go into the lab and we figure out, okay, well, how do we make these materials using very simple solution-based chemistry? So yes, we do make solid-state materials using solution-based chemistry. So again, it's a little weird. So then we take these solutions and we figure out, okay, if we want to take these particles and put them into a device or maybe make them into a coating for something, we figure out how we can take these particles and assemble them over very large scales and with very high precision. So in this case, what we're looking at here is a solution of gold particles, which we then put into a dielectric matrix. So this is a polymer here that we've then coated this this is a glass square with a bunch of these nanoparticles. So this is just a coating that we've been able to make. And again, this is not a typical way you would design a solid-state device. So normally when we're thinking about taking metals and semiconductors and building an integrated device or making some kind of functional material out of them, we usually think about this using top-down fabrication. So in top-down fabrication, what you would typically do is start off with your material of interest. In this case, it's a silicon wafer. Let's say we're making a computer transistor or something like that. And what you would do is you would take your bulk material and begin to carve out the components that you want. So in this case, you're carrying out a bunch of steps that are occurring in a very serial fashion. So we're patterning, usually by lithography. We're putting some kind of pattern down, and we're etching out our silicon wafer, and then maybe depositing a metal material on top as an electrode. So it's a very serial process that you do in a step-by-step procedure. And then in the end, what you would end up with is your entire patterned wafer. So there are some great things about top-down fabrication. The first one is that it's highly modular. So because you're doing everything in this very serial process, you can think about every single component, change out a component in case you want a different kind of semiconductor or a different kind of metal. You can do that without replacing your entire fabrication process. And also, the nice thing about top-down fabrication is that these tools are very readily available. For example, here at UCSD, we can walk into Nano3, take our silicon wafer, carry out these photolithography procedures, and get out our patterned device. But the problem with top-down fabrication is that you're very limited when you want to build a new material. For example, there are some materials that you just can't get as a bulk wafer. So you can't have this nice starting material, which then you can etch and deposit other materials on. And if you'll notice here, I've included this silicon wafer processing because it's planar. And if you want to build a material in 3 dimensions, it becomes very hard to do this using this planar fabrication process. So when we're thinking about building a new solid-state material or integrating these different semiconductors and metals into a new kind of device, it becomes really difficult to carry out this top-down fabrication if you want to build something that's 3D, something that has hierarchical materials properties, and also something that's tunable. So if you're thinking about changing the architecture of your material, it's very hard to do this using this kind of top-down procedures. So, and this is really where my group comes into play because we're interested in building new materials. And our main focus is on building new electromagnetic and optical materials. So the materials that we're specifically interested in come in the field of nanoplasmonics. So typically what we're looking at are small nanoparticles, typically less than 100 nanometers in diameter, composed of metals like silver and gold, so metals that have a large number of free carriers, or semiconductors like copper sulfides that also have a large number of free carriers. And so in nanoplasmonics, what we're doing is we're taking this particle that has a number of electrons, and we excite it with light, And what happens is the free electrons in our metal particle will start to oscillate in resonance with light. And what this does is it produces a very intense electromagnetic field that's essentially confined to this particle. So what this particle is doing, it's acting like a little optical antenna. So this is kind of crazy, right? Because now you have this particle, it's less than 100 nanometers, and it's confining light, maybe it's green light, that's 550 nanometers. So you're getting essentially a little antenna that's smaller than the wavelength of light itself, but it's able to produce this kind of confinement effect. And we're really interested in this plasmonic effect because we want to carry out things like optical spectroscopy. We can also think about using these particles to make solar cells and light-emitting diodes more efficient in terms of their optical absorbance or emission. We can also think about taking these particles and building something like an invisibility cloak. So this is kind of the area of metamaterials, which people are interested in. Or we can think about using them as sub-wavelength optics. So taking traditional optical material like a lens, and instead of using a large glass lens that you mechanically polish, instead you take a small nanoparticle there and use it to confine your light. So the interesting thing about these plasmonic materials is that, well, we found, okay, this one particle acts like a great antenna. But if you take two particles and put them together, now you have a material that's completely different. So with two particles, instead of getting this resonant oscillating charge wave that's confined to one particle, now you actually have this little nanojunction here, the gap in between two particles. And that, turns out, is a very good optical antenna. So what happens when you start building more and more of these particles, when you start putting more and more of these particles together? Well, that's really where my group comes in, because we're interested in figuring out how do we do this with these nanoscale building blocks. For example, how do we build a cluster of 4 particles where the junction is somewhere in the middle of this little tetrahedron? Or how do we build a 2-dimensional array that's well ordered so we get some kind of plasmonic crystal? Or how do we take this a step further and organize these nanoparticles into a complex 3-dimensional material? So while this is basically the kind of the basis for bottom-up fabrication, where we're taking these nanoscale particles and building them into the material we want, rather than taking this top-down approach where we're carving out the features that we want. So this bottom-up approach is really great because we're able to achieve complex 3D material design. And from the get-go, starting with our nanoscale building block, we can define our material, define the architecture, and thus define its function. But the hard part is figuring out, okay, what kind of materials do you use? So what kind of nanoscale building blocks do you want? And developing the tools for actually assembling and making these complex structures. So this is our area of research. And the first thing that my group has really done to kind of advance this field of nanoplasmonics is figuring out what kind of building blocks we want. So the first thing that we've worked on is essentially building a toolbox of nanomaterials that we can draw from to create these bottom-up architectures. And because we're interested in plasmonics, which is typically carried out with metal particles that have a lot of electrons, we've been able to carry out these chemical protocols for developing metal particles with different sizes and shapes. So this is kind of the first area that we work on, is figuring out how do we chemically synthesize metal or semiconductor nanocrystals using solution-based methods. These are some electron microscope images of a few of the different particles we're able to make. So these are silver spheres, gold nanorods. It's hard to see, but these are silver triangular prisms and silver cubes here. And the nice thing is that these are all made using simple benchtop solution-based methods. So we can make all of these particles in batch. And when you look at their optical properties, so if you look at this optical spectrum for all these different shapes, you can see that every time there's a peak here, it means that you're exciting a plasmon resonance. So all of these different shapes basically define the frequencies where you get a surface plasmon. So the frequency where these particles act as very good optical antenna. So we've basically shown that chemical synthesis can provide very good control over these kinds of solid-state materials at the nanoscale using these solution-based methods. Okay, so we have our toolbox of building blocks that we want to use to build our materials. So another area that my group works on is figuring out how do we take these nanoscale building blocks and assemble them into functional materials. And a really large challenge is being able to assemble these nanoscale particles over very large areas or very large volumes. So if you want to make an invisibility cloak, you don't want a single 100 nanometer section of your device that's invisible. You want to be able to do this over a very large area. And one way that we've been thinking about assembling particles is to use very simple dip coating methods. So these are methods that could perhaps be used over industrial size scales. And in this case, this is work that was done by my grad student Sue Wen, who has a poster today. What we've been able to do here is to take semiconductor nanoparticles. These are particles that display plasmon resonances in the infrared. And he's been able to carry out the surface functionalization of these particles such that they float at an air-water interface. So we're basically doing kitchen sink chemistry here. You can take an air-water interface, spread your semiconductor particles over this air-water interface, and depending on whether he's made the particles hydrophilic or hydrophobic using these capping molecular agents that you can put on the surface, these particles can either align into stacks, so these are disc-shaped particles, they look like little pancakes when you see them, or they can align side by side. So it's a very powerful way to assemble nanoparticles into different orientations over very large scales. And he's shown that using this air-water interface, he can assemble particles into monolayers, so these are monolayers with the two different orientations here, or into multi-layers, so over several hundred nanometers thick layers of these semiconductor particles. So in addition to assembling all of these building blocks over very large scales, we're also interested in being able to control how these particles are assembled at very small length scales. For example, again, looking at the junction in between two particles. And to do this, what we have to figure out is how do we program self-assembly at the molecular or the nanoscale level. And one example that we've been able to show is that the surface chemistry of these solid-state materials is extremely important to controlling how they come together. So this was some work that was published last year in Nature Nanotechnology. And what my student and postdoc showed was that if you take something like a silver nanocube, so again, this very anisotropic structure, and you coat it with polymers, you can explicitly dictate how these particles assemble together based off of very simple properties like polymer chain length, how densely these polymers are attached to the surface of your particle, and also the chemical nature of the particle. Is it hydrophobic? Is it hydrophilic? And again, these are store-bought commercial polymers, so we're not doing any really fancy chemistry. All we're doing is controlling how these polymers are grafted to the surface of our building block. So for these very long polymers, when we take all of our nanocubes, put this long polymer chain on the surface and throw it down onto a silicon wafer, what we see is that we can actually get our particles to assemble with a very specific edge-to-edge orientation. So this is an electron microscope of silver nanocubes that we've let assemble together in a polymer film. And you can see, if you look at this inset, that all of these cubes are aligned with their edges next to each other. And the gap here is the length of the polymer, which in this case is around 5 nanometers. So we have these 5 nanometer separations where all of our silver cubes are aligned with their edges. And now if you take a very short polymer, so in this case, the short polymer doesn't have these large steric interactions that this long polymer would. And we take the same cubes, now that they have a short polymer on them, we put them in a polymer matrix and throw them onto a silicon substrate and let them assemble. What we see is that all of these cubes align together with this face-to-face nanojunction. So just by changing the length of the polymer, we can explicitly control how our cubes actually assemble. And I should also mention that these junctions here, again, are controlled by the length of our polymer, which in this case is around 2 nanometers. So we're getting a nanoscale control over the junctions between our nanoparticles, not by changing the particle itself, but by changing the surface chemistry. And again, the reason why we're doing this is because if you look at these junctions, at these small nano gaps, we're essentially creating these optical antenna. So we're very interested in being able to explicitly control the size and orientation of these nanojunctions so that we can get out the right kind of light confinement properties. And if you're interested in this work, there's a poster by Matt Rosen, a grad student in my group, who's also down there today talking about plasmonic assembly. So finally, I wanted to tell you a little bit about where this kind of work is going. So in addition to using these materials as coatings or as optical elements, we're also very interested in building sensors out of these materials. And one area that we're interested in getting into is looking at biological systems, for example, cell membranes. So if you ever look at the kinds of drugs that are out there that target proteins, most of the proteins that are being targeted by drug therapies are actually targeting proteins that are inserted or somehow associated with cell membranes. So we're really interested in learning how cell membranes evolve and adapt when they're subjected to different, basically chemical entities and things like cholesterol. And so what we're interested in doing is taking our little optical antenna and being able to insert it into a cell membrane and optically probe how the membrane and the proteins associated with that membrane changes. So one thing that we've started doing is actually building these optical antennae so that they have basically a fake synthetic cell membrane that's on the outside. And so now we have our little antenna. It has some surface chemistry, and we've put this synthetic cell membrane on the outside. So now we can take a laser, come in, and probe the optical scattering off of our antenna and be able to get out some kind of signature of how this membrane is changing. And just to give you an example of how powerful this is some data that was actually taken about a week ago from one of my students for a couple of different particles that have these hybrid bilayers. And what you're actually looking at is a chemical signature of this bilayer structure. And if you look at this spectra, you see all these pairs of peaks. And what those pairs of peaks actually are telling you about the bond configuration for all of these chains in your phospholipids, so in the molecules that make up your cell membrane, and also in this synthetic part, this alkane thiol that we have around our optical antenna. And they're basically telling you how ordered that molecule is. So by looking at the ratio of intensities for each of these pairs of peaks, we can actually see these molecular conformational changes in our hybrid bilayer structure. And what he's showing you in this spectrum is that depending on how long or short this little inner part of our bilayer is, you can actually see a change in the molecular conformation of the phospholipid membrane that's surrounding it. So if you're interested in looking and learning more about how we use our optical antenna in this kind of spectroscopic application, there's a poster by my student Tyler Dill. Go ask him hard questions. So finally, I want to close with this take-home message that nanoscale self-assembly can offer rational, predictable routes for building new functional solid-state materials. And I'd like to acknowledge my entire group, as well as my collaborators, Gaurav, Arya, and Mike Saylor, as well as funding sources. If you'd like to be added to those lists, you can come talk to me afterwards. And thank you for your attention.
Are there any questions for Dr. Tao? I've got a couple, actually.
Sure.
So at the beginning, you talked about the materials and how you're trying to make structures, like lattice structures, and how it's changing properties.
Mm-hmm.
What's the advantage of having a lattice structure of your nanomaterial versus just a monolayer or just individual optical antennas? Because it seems like you get a signal as soon as you have your optical antenna forming. So do you get an amplification signal? What is the
Yeah, so it really depends on the application that you're looking at. So if you want to do something like optical spectroscopy, having one particle is fine. Your signal is going to be pretty low. So having maybe a denser array of particles would help. But if you're interested in creating something like an invisibility cloak, so there are these things called metamaterials or negative index materials, where basically you take a periodic array of these metal structures and shine light on that. And what that does is it actually sets up a propagating wave inside of your structure. So if you want to make a material that can reflect back a very specific wavelength or transmit a specific wavelength, you would need a periodic structure. So it really depends on the kind of application that you're trying to design your materials for.
Does the periodic structure affect the absorbance of the light that you're getting into the structure? Because as soon as you have those other that lattice structure, you're now preventing the movement or the actual association? Of
Absolutely. What you're doing is you're coupling two particles, or in the case of an infinite lattice, an infinite number of particles together. So it's no longer a single particle system. And that's why you get these interesting nonlinear effects inside of a periodic structure that you wouldn't see if you just had a random array of particles or a single particle.
When you're talking about the cells at the end,
Mm-hmm.
and you're probing the phospholipid, or the actual association of phospholipids to your polymer with your optical antennas, you were talking about the association of those amongst themselves.
Mm-hmm.
So do you think that when you put those within a lipid bilayer, whether it be a red blood cell, for instance, for a simple system where it's pretty much all just lipids around there, do you think you're actually going to probe the fluidity of the membrane? That you're going to get information on the association of your phospholipids with the surrounding phospholipids? Because a phospholipid ball doesn't necessarily associate very well with a phospholipid monolayer or bilayer.
Right. So actually, people have done these studies with non-plasmonic particles, with things like silica beads, and they do probe things like the fluidity of the lipid layer. But with those kinds of structures, it's very difficult to get any kind of chemical signature from your optical output. So what they can look at is scattering off of a bead, how the refractive index changes when you put a lipid bilayer on there. So we can certainly do the same thing. The lipid bilayer is actually fluid on the surface of our particle. But with our particle, what we'd actually like to do is to get a chemical signature. So we'd like to probe the actual molecules that are inserted into the phospholipid or the phospholipid molecules themselves and look at conformational changes.
So then would you think that things like cholesterol would start to migrate into or around?
Yes. So things that would change the structure of your membrane, things like cholesterol that would make your membrane more rigid. I would certainly expect to be able to see that using our this enhanced spectroscopy technique.
And I guess just the very last question is, if you have two of these little silver phospholipid, I call them micellar for lack of a better word, would they then interact with one another? Do you have any kind of charge or any kind of interaction between them? Would they self-assemble despite having this coating or buffer around them inside your membrane of your cell?
Yeah, you know what? I'm not sure about whether there would be some natural aggregation in solution. All of our particles we put down on a substrate, which is how we know that the lipid membrane is fluid over the particles. But certainly you could design a phospholipid to do that, which is, it would be in line with what we're interested in doing, so maybe.
Great.
Can you design, so you can design them to bind and interact with the small molecules other than lipids?
We've only tested phospholipids right now. I have seen work with silica beads where they put charged groups on the surface and they can show that the particles do aggregate. But as for small molecules, I'm not sure about that.
And just talking about the size of a silver ion, is it just one ion that's encapsulated in your micellar?
One particle.
One particle.
So it's an uncharged neutral silver particle.
Okay. What is the size of that particle relative to the size of your phospholipid around there?
So the lipid vesicle, or the phospholipid membrane, is pretty closely attached. The size of the particle can be anywhere between 30 and 100 nanometers. So it's very large in comparison to an individual phospholipid molecule.
So then you could imagine the cell endocytosing then your your vesicle instead of possibly interacting with it.
Yeah, and in fact, that's what happens when you actually put particles into cells. They'll actually become endocytosed. So
I'm sure there's plenty of people in the mechanical engineering department who are interested in doing a cytoplasmic rheology, probably interested in your types of particles.
They should come talk to me.
Thank you very much.
All right, thank you.